Welcome back in. We're going to spend the next two little videos talking about hemostasis, or how our body responds to when there's an insult or injury to tissue and how we stop that bleeding from happening. To start off with, we're going to look at a few definitions. We're going to need to look at the difference between autocrine and paracrine chemicals and how they react upon neighboring tissues. Specifically, we're going to concentrate today on prostaglandins, of which we have thromboxane, A2, and prostacyclin that are going to be involved in that clotting factor or process. And then several other chemicals, CD39, which is going to be involved in that too. I just wanted to point those out to you. I'm going to have you look at three different stages of clot formation, and then we're going to detail the first two stages of that, specifically looking at vasoconstriction and platelet aggregation, and that's what we're going to concentrate on today. So let's take a look here. All right, so hemostasis. Definition: the cessation of bleeding when a blood vessel is damaged. So stasis means still, right? So it's not moving at all, and hemo is referring to our blood. So it's basically just meaning still blood. Normally your blood's traveling through the body, so hemostasis is preventing that blood from bleeding anymore. Damage, when there's tissue damage, you're going to have this endothelial layer, and if that endothelial layer gets cut, then the first thing that's going to happen is we're going to have vasoconstriction, and that's because serotonin is going to be released, and that serotonin is going to cause the vasoconstriction, hopefully reducing the flow of blood to that area. Then we're going to make a platelet plug. So platelets are going to come in here and fill that thing in, and that's just kind of a temporary hold or fix until we can get fibrin in there, and the fibrin is going to make this really sturdy web, and that's what's going to be catching all these different blood cells and things to make a big clot. And so when you see a blood clot, that's due to the formation of this fibrin protein web. So we're going to concentrate today on these two parts, the vasoconstriction and the formation of that platelet plug. So first, we've got a couple definitions we need to go over because they're going to be helpful in understanding what's going on a little bit later. We've got autocrines, and autocrines are chemicals that are released that regulate the same type of cells in the same organ or neighboring cells. So you can think of, like, with the endocrine system, we had hormones, and hormones are being released and go throughout the body and flood the circulatory system throughout the entire body. Autocrines are chemicals like hormones, except that they only stimulate the same type of cells in the same organ. And so they're releasing them, and they have receptors on themselves, or the cell right next to them that's the same exact kind of cell. Those are autocrines. Auto means self. So they're self-stimulating. Next type are called paracrines. And paracrines are chemicals released that regulate different type of cells in the same organ or neighboring cells to them. So now we're having these little chemicals released, and they're going to another cell. But again, it's all within the same organ. And this is different than our endocrine system that releases hormones. And remember, those hormones are going into the blood and going to different distant places, distant organs, different distant tissues. So big difference between autocrines and paracrines. There are many different types of paracrines. I'm just going to mention two types to you today. One are cytokines, and cytokines are involved in the immune response. And I'm bringing this up now because when we start talking about the respiratory system, we're going to see how cytokines are involved with COVID. And so we'll be bringing some new information to you there. They also act in growth factors. They're throughout the body. Most of these paracrines you'll see in organs and tissues throughout the entire body. Today, we're going to look specifically at prostaglandins. And prostaglandins are a type of paracrine or autocrine regulators, so they're chemicals. And the big thing about prostaglandins is that they're released from the plasma membrane. So we're going to see these prostaglandins being released from things, from many different organs. Again, immune system, reproduction, GI, all of these organs are releasing prostaglandins that are paracrines. And what's special about these guys is just their makeup. they've got this big long 20 carbon long fatty acid chain that in the middle of it is going to have this 5 carbon ring. And so that's kind of what they look like. They almost look like those phospholipids that we saw earlier, except they're just a carbon fatty acid chain. So there are a couple of different types of prostaglandins that we're going to look at with as related to blood clotting. And these prostaglandins will have many different effects throughout the body. But the first one that we're going to look at is called prostacyclin. So prostacyclin, it's also called PGI2, is a prostaglandin, so it's a paracrine as well, that inhibits platelet formation and causes vasodilation. So it's doing these two things. It's inhibiting platelet formation, and if it's vasodilating, so it's doing the opposite of making a plug here. It's allowing the blood to flow freely. The opposite of that is going to be thromboxane, and there's different types of thromboxanes. We're going to concentrate today on thromboxane A2. This is a prostaglandin that does the opposite of prostacyclin. So it's going to promote platelet aggregation. So this is what you're going to want when you want to make a clot, and it's also going to cause vasoconstriction. So we've got these two prostaglandins that are opposing each other. We're going to see how they play out in our system here. I kind of wanted to bring up COX inhibitors because you may have heard about them before. A COX inhibitor is inhibiting COX enzymes. So COX really stands for cyclooxygenase. So cyclooxygenase is an enzyme, and it's needed to make these prostaglandins that we're talking about. So platelets are going to be responsible for making thromboxane A2. Thromboxane is also made in the stomach and in the kidneys, and it needs this COX-1 enzyme to make thromboxane. Similarly, and that's done, so we're going to be looking at these platelet cells that are making this thromboxane A2. Similarly, endothelial cells are going to be making our other prostaglandin, our prostacyclin. And those are made by a COX, we call it COX-2 enzyme. So that COX-2 enzyme is going to make PGI2 or prostacyclin, and that's going to be our vasodilation. So this is going to cause free blood flow, while thromboxane A2 is going to basically start our clot. Now, the reason I bring up COX-1 and COX-2 is because I mentioned a minute ago, you may have heard of COX-1 and COX-2 inhibitors. Well, our NSAIDs, non-steroidal anti-inflammatory drugs, can make COX inhibitors. And the most common one that you've probably heard of is aspirin. Aspirin is going to inhibit COX-1. So by taking aspirin, low doses of aspirin every day, people can limit the effect of having or limit the risk of having a heart attack or a stroke because they won't be making this thromboxane A2 as much, so you're not going to be vasoconstricting or causing aggregation of those platelets. So that's how aspirin is kind of working. We have COX-2 inhibitors as well, and COX-2 inhibitors were initially made for involving the mucosa of the gut lining and reducing some problems there. But unfortunately, what they found out with, and I remember when I was working in home health, like this big announcement came out one day because a lot of people were using Celebrex and Vioxx for a multitude of reasons, and they realized that inhibiting COX-2 actually inhibited the vasodilation and the anti-aggregation effect, so people were ending up getting more clots, and they were having a higher risk of heart attacks and strokes. So they shut down Celebrex and Vioxx for a while until they could make some modifications there. So that's a little tidbit on how our COX-1 and COX-2 are involved in making these prostaglandins. Okay, So let's get going about what these platelets are and blood vessels are doing to start the clot. Normally, we're going to have prostacyclin, or PGI2, and nitric oxide as well, which do two things. First, they're both going to be involved in vasodilation. That's going to be really key. So we're keeping those blood vessels open so blood can flow. And then PGI2 specifically is going to be inhibiting platelet aggregation. You don't want platelets aggregating all the time unless there's an injury. So it's allowing these platelets to just flow through the blood, sliding off each other easily. There's another enzyme that's sitting on the endothelial layers, and this is called CD39. CD39 is going to be key in that it breaks down ADP. So you know you've got ATP and ADP, adenosine diphosphate, throwing through your plasma all the time. ADP is really sticky for platelets. So if you have a lot of ADP around that endothelial lining, it's going to cause platelets to stick together. So CD39 breaks down that ADP into AMP and inorganic phosphates, and this inhibits platelet aggregation. So let's take a look at this so you can kind of get and see what's going on. So this is our normal vessel. Here you've got your endothelial cells kind of lining the blood vessel here. Down below that, so the layer underneath the endothelium, you're going to have a bunch of collagen that you can see here, these big long yellow tubes of collagen. I'm going to draw these in green. And you've got something called von Willenberg factor, which we're going to see in a minute. This guy right here, all these little blue dots that are holding that collagen together. So normally, endothelial cells are releasing prostacyclin, PGI2, and nitric oxide. And these two things are going to cause vasodilation and inhibit the platelets from aggregating together. Then we've got this CD39. And CD39 is an enzyme that's lining all of these endothelial cells. So you just got to imagine them along this whole thing here. And that CD39 is causing ADP, which is really sticky, remember, to change into AMP plus a little PI. We break that off here. So then that AMP is not sticky, and again, the platelets don't stick. That's the big thing here. Now, when we get an injury, here's what's going to happen. Notice that we lost that endothelial cell. Before we had an endothelial cell here with all those CD39s, but now that's gone because we've just injured it. So what's going to happen is that we're going to have the collagen down here is exposed because it doesn't have that endothelial lining over it. If the collagen is exposed, the collagen is going to bind all of these platelets out here. So here's some platelets floating around. That collagen is going to bind to those platelets, and those platelets are going to be held to the collagen by that von Willenberg factor, or von Willenbrand factor that I just mentioned in the last slide. So the platelets are being stuck there, and the platelets are going to form this little plug, and they're going to do a couple of things. Well, one, if we don't have the CD39, then there's going to be ADP, and that ADP that's there is going to allow those platelets to stick together a little bit better. So they're not only sticking to the collagen, but they're sticking to each other because we have all of this ADP. The platelets are also going to release serotonin, and serotonin is going to cause vasoconstriction. So that vasoconstriction, that in this local area where we've got all these platelets aggregating, the vessels are going to clamp down and stop, or at least try and reduce the bleeding. And then they're also going to release thromboxane A2. And that thromboxane A2 is also very sticky, and that's going to cause these platelets to clump together as well. All of this is coming down to initially try and slow down that bleeding until the big guns can come in the fibrin to really make the clot. To get that fibrin in there, these platelets are also going to, this whole process here is going to release a plasma clotting factor. And there are a bunch of clotting factors that you're going to see in the next slides that are going to come out and cause the whole fibrin process to come in and make our clot. And that should conclude this section.